Welcome to part 3 of this series of data fitting series, and in this part we look at polynomial models, quadratic and cubic functions. These models handle curves and bends that linear models cannot capture. When your data curves, you need a polynomial model. These add curves and bends by including terms with x squared, x cubed, and so on. The simplest polynomial is the quadratic, that is degree 2. It creates a parabola shape. So to make this easier to imagine, think of a ball thrown in the air. It goes up and up, and then it reaches a maximum. And of course, because of gravity, it will come back down. That is a parabola. So there is a one turning point. The quadratic equation is y equals a x squared plus b x plus c. This creates a parabola shape. The key parameter is a. If a is greater than 0, so which means it's positive, the parabola opens upward like a U shape. If a is less than 0, which means it's negative, it opens downward like an inverted U. So use when your data has one turning point. Quadratics appear everywhere in science and engineering. For example, in projectile motion. When a ball is thrown in the air, it follows a parabola, as mentioned in the previous introduction to this model. Another example is optimization problems, finding maximum profit or minimum cost, and also in machine learning applications. Also, when we look at area versus side length of squares. Another example is braking distance versus speed. So when you double your speed, you quadruple your braking distance. For more complex curves, we go to cubic, which is degree 3. The equation is y equals ax cubed plus bx squared plus cx plus d. Cubics create an S-shaped curve and can have up to 2 turning points. You should use this when your data has 2 bends. Here you can see a typical cubic curve. Notice how it has that distinctive shape with 2 bends, which we mentioned early on. The curve goes up, then down, then up again. Examples of this trend include certain phase transitions, complex kinetics, and in pharmacology applications, some dose-response relationships. So here is a practical rule. The polynomial degree equals the maximum number of bends plus 1. So a linear with degree 1 has 0 bends, so it's a straight line. Quadratic with degree 2 has a maximum 1 bend. And the cubic with degree 3 has a maximum 2 bends. Quartic with degree 4 has maximum 3 bends. And so on. But you need to be careful here, because higher degree polynomials can wiggle wildly. And that means they can have really many bends in there. They can really fit all your data, and they can go and fit all points, go through all your points, and that can lead to something we call overfitting. And we'll look into this later on, because that could be quite dangerous, because it means you're not really getting the real the actual thing about your data. You're just fitting the data, but you're not understanding the underlying fact behind your data. Let's look at this classical quadratic example, which represents a projectile motion. So in this example, the ball's trajectory is a parabola. The maximum height occurs at the vertex, which you can find using the formula t equals minus b over 2a. So the negative coefficient here means the parabola opens downward. The ball goes up, then comes back down. So the quadratic fits data with one turning point perfectly. So let's look at this pharmaceutical application, and in this example as we have tablet compression. So we're trying to optimize the process of tableting. So in this case, hardness equals A times F squared plus B times F plus C. And in this case, F is the compression force. If you plot hardness against compression force, you will get a curve. So too little force, and that leads that the tablet will become soft or friable. And the opposite is correct, because too much force, and then you will get capping problems. So fitting a quadratic kind of fitting lets you find the optimal compression force at the vertex. So this is a response surface methodology application of such optimization process. Let's look at this other example using DSC, differential scanning calorimetry analysis. So in order to get accurate enthalpies, we need to get proper baseline correction. So the heat capacity is not constant, especially at longer range. So it will change with temperature. So the equation Cp equals A plus Bt plus C T squared gives a polynomial baseline. So that means accurate baseline that will of course give us an accurate value for delta H. So this is very important because used for enthalpy calculations in melting and crystallization analysis.